So we started out by looking at this as, can we find the slope there? I think it's interesting that they put a car on the edge of a cliff up here. Okay, I'm not really sure the purpose of that, but that makes me nervous that it's a car on the edge of a cliff. So it says the graph of y equals f of x can be seen in Desmos, is also shown below. Which x values is it not continuous? Okay, where is this function not continuous? -2. Oh, writing with a highlighter, that's not going to work. At x equals -2. Why at -2? Okay, it's a jump discontinuity. And then where else? At +2, and what's going on there? It's a removable discontinuity or a hole. Okay, so that is correct. Okay, all right, so let's find the rate of change between 7 and 9. All right, it's a linear piece, so we can find that rate of change. What's it going to be? Yeah, my rate of change is -1/2. All right, it's a constant because I have a linear piece right there. Then it says, hey, do the same thing between 9 and 11. So what's the rate of change between 9 and 11? 3/2. Okay, so again, we're making an assumption here, and then we're going to see if it's right. What about the rate of change at exactly 9? What would you think it might be? If we've got, it's -1/2 on one side, 3/2 on the other, what would you think maybe it might be in the middle? Because we didn't include 9 in either one of those intervals. Any thoughts? Okay, so in Desmos it says -0.5, all right? So maybe it's that, okay? Could it be that it's somewhere between -0.5 and 3/2, since we've got two different slopes on each side? All right, so there's a lot of options there, okay? So maybe between the other two. Desmos says it's -1/2. All right, we'll find out if Desmos is lying to us here in just a second, okay? So yeah, that's exactly what I would have done on that. All right, so now it says to write an expression that could be used to estimate the slope, and that's the key word right there. Estimate the slope of the tangent line right before x equals 1, okay? So we're going to kind of do this in two pieces, all right? So we're going to do the rate of change before x equals 1. So we might use the ordered pairs, so like 0.99 for x, and then maybe 1. Or 0.9 and 1, it doesn't matter, okay? And if we do the rate of change, so f of 1 minus f of 0.99, we divide it by 1 minus 0.99. This is where you wanted to use Desmos and put those numbers in to get y values, okay? Switch over here real quick, okay? So this is where we might want to put in f of 1, and it gives me 6, and then we could go back and do f of 0.99, and that gives me 5.9202. So it can give me those values to plug in, okay? So if we go back and we plug those in, you should get about 7.98, okay? So it tells me that the slope, this is my average rate of change as I get close to 1, is about 8. Okay, so coming from the right. All right, so if we're estimating that slope coming in from the right, that's a limit. Okay, so we're taking the limit as x approaches 1. Sorry, that was coming from the left. Rate of change means I'm doing the derivative. And we got that was about 7.98. Right? So that's what we did there. We did a limit. All right? Now it says, hey, let's do it again, but this time come in right after. Okay, so we're going to come from the right this time. So my ordered pairs that I might use are 1 and 1.01 for my x values. Okay, so again, using our Desmos to get our actual numerical values. All right, if you do that one, all right, again, that's an average rate of change. We should get about negative 1.997, something like that, okay, for my average rate of change. That too is a limit, okay, because I was getting close to 1 from the right. It's my derivative because it's the slope of my tangent, and we got negative 1.997. Okay, so on one side, the slope of my tangent is 7.98. On the other side, it is negative 1.997, and those were limits because we got as close as we could possibly be. All right, so the next question that it asks you on the next page is, what's the slope at exactly 1? Well, we're having to limit to get close to 1. Are my limits the same on each side? No, and what does that mean? It doesn't exist, okay? It means it doesn't exist. This slope at x equals 1 does not exist, all right? And the reason why is the left and right limits are not equal. Okay. All right, so then it tells me to go back and to turn on the folder that's labeled tangent line, okay? And it's move the slider for A. What do we notice as we do that, okay? So if I go back over here and I turn the slider back, turn the folder on, okay? And I've got my slider and I can just move it. Hold on a minute. There it is. So I can move my slider. Let's go over here and let's talk about it 1. So it's like, I'm good, I'm good. Oh, and then all of a sudden it just switches. I'm good, switch. I'm good, switch. All right? Does it do that anywhere else? I'm good. It's just following the curve. I'm good, switch. I'm good, switch. All right? So we've got these. Now notice this point right here, it doesn't do that. What's the difference between this point right here at 5 and this point up here at 7? Yeah, how sharp the turn is, okay? So when I get up here at 1, I've got this really sharp turn, but if I'm over here at, whoops, too far, negative 1, it's not a sharp turn, okay? Think about a roller coaster. This would be okay in a roller coaster, right? It would take my tummy, but it'd be okay. But if I go up here, whoo, like I'm just falling off the edge, right? We would call that a super thrill right there, all right? Like that roller coaster at Universal where it comes straight out and then whoo, it just drops you. No thanks, all right? That's a no, solid, hard pass for me. Okay, so that being said, the tangent line follows the curve. Okay, follows the curve, but it jumps at the sharp points. And that's going to be important, I think. Okay. Then it tells me to find the exact value of the slope of the tangent line at x equals 3. Explain our method. Okay. And so that's kind of nice over here. If I want the exact slope, I could do f prime at 3. Okay. And it tells me that it is negative 1, and that's what I would do. I would use Desmos to do that for me. Okay, so we could just evaluate f prime at 3 is negative 1. Okay. Now, looking at your graph, at which x values do you think the tangent line has a slope of 0? Where do you think it has a slope of 0? Okay, it's got to be somewhere that we still see the line, right? 0 slope, remember, is a horizontal, too far. It's a horizontal line. Okay, so it looks like it's happening at negative 1, And where else? At 5 maybe. Yep, we're looking at the x value. Okay. Looks like we got a slope of 0. Okay. So x equal to -1 and x equal to 5 because our tangent line is horizontal. Yes, okay. And why is that? Yep, because it's a constant. It's already has a constant, right? And so if we push it back over there, okay. So that whole line, it was already horizontal. Okay, so it too would have that. Yeah, good. Good recognition there. Okay. And then we would say when x is between what, -4? It wasn't -2? Ah. Yes. Okay. Okay, so at which x values does the graph have a turning point? In other words, where does it turn directions, change directions? All right, let's look. All right, it's going to change directions here. All right, so that's at -1. It's going to change directions at +1, at 5, at 7, and at 9. Okay, so it's changing directions at all those points. Okay, so it changed directions in terms of where it was going. Right? So we have -1, 1, 5, 7, and 9. Okay. So where did we have those sharp turns? Okay, so not the smooth ones where the tangent line still showed, but where were the sharp ones at? 1, 7, and 9, okay? Well, we already said at 1, the derivative, the limit, doesn't exist, right? Because it was different from both sides. So here, the slope does not exist. The same is going to be true at these others. Okay, so now it says, imagine if we created the slopes graph of f. We want to list a few ordered pairs that would be on the slopes graph, okay? Well, we already did a couple of those in the first thing, all right, where we said like between 7 and 9, okay? So if I go between 7 and 9, just looking at my tangent, let's go over here, all right? So at 8, what would the slope be? It's on that -1/2. It's on that linear piece. If I went to, let's say 10, what would the slope be on that piece? 3/2, right? We already did that. If we go over here to -3, what would the slope be? 0, okay? And then we already said at -1, it would be 0, right? So we're just picking some slopes off the graph that we could see. So we said at... At 8, it was -1/2. At 10, it was 3/2 because we'd already collected that slope. At -1, it was 0. At -3, it was 0. So just picking some points. Okay. Now, let's talk about where the slopes graph would have discontinuities. Okay. Where would there not be a slope? Okay. Where would there not be a slope? So let's think about it. All right. Where would there not be a slope?
X equals 1.
Yep, for sure at x equals 1, right? Because we already said that's where that sharp turn is. All right, anywhere else? Oh, what happened when I got right there to the hole? My line disappeared, okay? So that means there's no slope right there, okay? Because the line disappeared. All right, I'm good until I get back over here to this sharp point, and then my line disappears. It's quick. You can't see it because it totally switches. Same thing over here. All right, is there anywhere else that the line kind of disappears or switches? At -2, okay? So we would have discontinuities at x equals -2, at 1, at 2, at 7, and at 9. The reason that happens is because the slope does not exist there. Okay? Our slope doesn't exist at those points. So we could always have a slope of 0, but we can't have a slope that's undefined, okay? And so if you go back and you look at that graph that we started with, I'm going to go back over here and look at this for a second, okay? We know that our slope graph was going to have discontinuities here, 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 and here. What's happening in all those places? What's happening right here on the original picture? There is a jump discontinuity. So a jump discontinuity means no derivative. Okay. What happened up here at 1? It's that sharp turn, right? We actually refer to this as a cusp. All right, it's a cusp because it's curved going into that sharp point, okay? So there is no derivative, okay? At 2, we had a hole, so there was no derivative, okay? Again, over here at 7, we would call that a cusp because it's curved on one side, okay? It's that sharp turn. It's a cusp, so no derivative. What's different about it, 9? We know there's no derivative there, but what's happening? Yeah, they're both linear, so we call that a corner. So there's no derivative. Okay? And that's the main purpose of today, is knowing where do we have functions that are not differentiable. Okay? What does it mean to be differentiable? How do I know when I'm not differentiable? All right? And so that's what this whole exercise was about, was looking at that graph and looking at the slopes and seeing what's going to happen. Okay? So let's pull this all together and talk about what your questions are going to look like. Okay? And how we're going to check for differentiability. So we had a jump discontinuity, we had a cusp, we had a hole, another cusp, and we had a corner. Okay? So all those places, the derivative is going to fail to exist. Okay? All right, so differentiability. Okay, differentiability. What that's saying to us is that, I won't use that color. All right. Differentiability refers to where a derivative exists. Okay, differentiability is where a derivative exists. We're going to talk about specifically at a point. Call it x equals a, okay? There are 2 qualifications that must be met. The first is this, okay? F at a must exist. So there has to be a function value at that point, okay? So there has to be a value for the function. The second one is that the limit of the average rate of change coming from the left must equal the average rate of change from the right. Okay, so the slope from the left must equal the slope from the right. Okay, so that's what we did with that around 9, where we looked at those different slopes. Okay, so the limit of that slope. Okay, so slope from left must equal the slope from the right. Now, special caveat, there's no derivative at an endpoint. We can have a limit at an endpoint, but there's no derivative at an endpoint. Okay, so let's do one where we prove differentiability, all right? Using the definition. Okay. So first part of the definition, f at a must exist. The a we're talking about is -1, all right? So f of -1 has to be a value. Well, actually, it's g, sorry. Okay, which would be -1 squared, which is what? Okay, it's 1, so we met the first qualification, all right? In continuity, the limits have to equal that function value, all right? Not so in differentiability, all right? So now we're going to do those two limits that we need. Part 2 says we're going to take two limits. We're going to do the limit as x approaches -1 from the left, all right, of g of x minus g of -1 over x minus -1. So that's my first limit. And then my second limit as x approaches 1 from the right, or -1 from the right, g of x minus g of -1 over x minus -1. Okay, and it may seem a little redundant that we'd have to do it from both sides. Like, when would it ever be different? Okay, but there are times where it will be different. All right, so that's why I want to show you this. So we're going to keep our limit notation. So limit as x approaches -1 from the left. G of x is x squared minus -1 squared, which would just be 1, over x plus 1, right? If I evaluate that limit, we would plug in -1. What's going to happen? If I plug in -1, so I've gotten to this point, if I plug in -1, what would happen to that function? It'd be 0 over 0, which you can't have, all right? So we're going to have to factor, all right? Luckily, this one's one that's going to factor nice. So limit as x approaches -1 from the left. The top's going to factor into x plus 1, x minus 1, over x plus 1. Sure enough, I'm going to lose, all right, that first parenthesis. And now I just plug in to what's left. So that would be, drop my limit, -1 minus 1, which would be -2. Okay, so that's my first slope. Okay, so slope from the left is -2. We're going to repeat it from the right. So limit as x approaches -1 from the right. Okay, g of x is x squared. G at -1 is 1 over x plus 1. Did the process change at all? No, we got the exact same thing. So we're not going to redo all the factoring and stuff, okay? We know that when I do that, because it matches what's on top, it's going to be -2, okay? So now, is this differentiable at x equals -1? Did we meet all three requirements? We sure did. So yes, g of x is differentiable at x equals -1. I'm going to let your work speak for it so we don't have to put a proof statement in there. Okay? So that's how you prove differentiability. Okay? So now I want you to try one. All right? It's absolute value. Okay? It's absolute value. And we're doing absolute value at 0, okay? Anytime we work with absolute value, what do we have to do? You have to do two functions, okay? We have to define f of x equal to absolute value of x as x when x is greater than 0, the opposite of x when x is less than or equal to 0, okay? So see if you can do that one, all right, using the proof state, okay, all three statements that we just had to do. Is it differentiable at 0? Is it the pig's birthday? Oh. Oh, okay. Okay, so let's look at this. We got to do these two limits, okay? We got to approach 0 from the left and 0 from the right. If I'm approaching 0 from the left, which piece of my function am I going to use? The bottom piece, okay, where it's the opposite of x. So I have the opposite of x minus 0 over x minus 0. Well, that's just the opposite of x over, oops, need my limit. That's just the, I was getting excited. Limit as x approaches 0 from the left, sorry. Okay, that would just give me the limit as x approaches 0 from the left of negative x over x. Well, those x's are going to cancel out, and what's going to be left? Negative 1. Okay, be negative 1. We're going to repeat it from the right. So limit as x approaches 0 from the right. If I'm coming from the right, I'm using just the plain old x. So x minus 0 over x minus 0, which would just give me the limit as x approaches 0 from the right of x over x, which would just be what? 1. Do those two limits match? Nope, those are not equal, so it is not differentiable. F is not differentiable at 0. Okay, which, knowing what we know about an absolute value function, what happens at 0 in an absolute value function? Yeah, there's that corner. Okay, so that's why. I've already purchased from you. Thanks for asking. Okay. So now let's talk about where things are not differentiable, all right? We labeled those a few minutes ago. We were like, hey, it didn't work when we had a discontinuity. So that's the first place. Any discontinuity, okay, of the function. So those are your jumps, your holes, your vertical asymptotes. okay? So a function is not going to be differentiable anytime we have any of those things, right, in those places. The second one we talked about were those sharp points, which is the corner. That just means it's linear on both sides, okay? So two linear pieces. All right, that would be like your absolute value coming together, okay? And what's going to happen there is that your two limits are going to be opposite signs. So like in your absolute value, one was positive 1, one was negative 1. If it's a corner, the derivative would be positive 1/2 on one side, negative 1/2 or the other. Or they're just going to be opposite signs. They may not be the same value, but they'll be opposite signs, okay? Then you have a cusp, all right? And a cusp is where we're going to have curves that come together in a sharp point, okay? It could be a linear and a curve, or two curves that come together. So it might look something like that, or it could just be, oh, I'm gonna go the other way. Something like this, two curves that come together. So we would not be differentiable at those points. Okay. Now, there's one more that we didn't actually see in the exercise we did today because it's kind of rare. And anytime that it happens, it's typically given to you in verbal form. It's called a vertical tangent, right? And the best way I know to explain that is like a cube root function. Does anybody remember what a cube root function looks like? So cubic is the snake. What was cube root? Yeah, we turn it sideways, walk like the Egyptian, right? And so if we think about that, it has this kind of almost linear piece there in that middle. That would be what we refer to as a vertical tangent, okay? Almost always it's a verbal description when that happens because it's very hard to see on a graph, okay? It's a verbal description usually in any of the problems. Like I said, it's the least frequent in terms of ones that are used. Typically, it's a discontinuity, a corner, or a cusp. Okay, in terms of what we'll see. Okay. So just like they may ask me, where is it differentiable? They might also say, where is it not differentiable? All right, or prove that it's not differentiable. Okay. Now, I'm not going to work through all the math on this next one just because it takes a hot minute, okay? But we can look at this picture. It tells me to compare the right and the left-hand limits to show that it's not differentiable. What issue do we have going on at 0? What is going on right there? It's a cusp, okay? It's a cusp. If I did the two limits, okay, I would do the limit as x approaches 0 from the left. It would use the function x squared. So that would be x squared minus 0 over x minus 0. Okay, so I'd use that function, right? If I was coming from the right, I'd do the limit as x approaches 0 from the right. This time it's just f of x. So x minus 0 over x minus 0. Okay. They would work out to be, one would be 0 and the other one would be 1. Okay, or negative 1. So that's why they did not work. All right, but that's what you would do to show it. Okay, so you'd use the function on the left, the function on the right. Okay. All right, so let's look at these next few because I think these get easier as we do them because we can think about what we know about the function. All right, take a look at this next one. Oh, apparently I skipped all that, did I? Oh, no, it's down here. Sorry. Okay, it says find all points in the domain of this function where f would not be differentiable. Tell me what you know that function is if you were to graph it. It's absolute value, okay? Which means it's a v. So basically, I just got to know where's the vertex, okay? So if I were to graph this absolute value, where would I send it? I'd send it right to and up 3, okay? It wants to know values of the domain. So do I care about the y values? Nope, I just care about the x. Where is it not differentiable? At x equals 2. Okay, So that's all you'd have to do on that one. Okay, where is it not differentiable? X equals 2. Okay. All right, so here's our important theorem. Okay, it's why we can say what we say when we say it. All right, here it is. Okay, if f of x has a derivative at x equals a, then f is continuous at x equals a. Okay, this is that whole big concept of differentiability implies continuity. You will be able to use that as a justification always. All right, now, the thing that gets people is the converse is not true. Just because something is continuous doesn't mean it's differentiable, that there's a derivative. Think about your absolute value. It's continuous, but is it differentiable everywhere? Okay, it's not. It's not differentiable at that. Okay, so the converse is not true, and that's important. If it's continuous, great, but it doesn't mean there's always a derivative everywhere, okay? If there's a derivative everywhere, then it is continuous. Thank you very much, okay? Because we can't have a derivative at a discontinuity. All right, let's look at this one, okay? It's important to remember the definition because if we pay really close attention, we can skip a lot of hard math sometimes, okay? It says, is this function differentiable at x equals 1? What's the first thing we have to check? H at 1. Is there a function value at 1? Okay. Is there? No. Why not? Yeah, 1's not in the domain of that function. Okay. So H of 1 is not in the domain. Okay. Actually, we'll say H at 1 does not exist. Let's say that. Therefore, H of x is not differentiable at x equals 1. So lucky for us, if we know that part of the definition, we're good, because here's what would happen. If I did the derivative from each side, they would equal each other. Okay, so we have to know that we have to check the value of the function first. Okay, because it'll lie to you. Okay, everybody's favorite. How do we do a derivative on the calculator? All right, we've been living for this moment. We don't get to use our calculators often, but when we do, we want to use them to their full effect. Okay, so calculator keystrokes for finding a numerical derivative. All right, it is Math 8. And it says in deriv. Okay, it will not tell you the derivative in terms of if f is x to the 5th minus 27. It will not tell you f prime is, 5x to the 4th, let's say. All right, it won't tell you that. But if it asks you, okay, f of x is x to the 5th minus 27, what's f prime at 2? It'll tell you that. Okay, so it will tell you that. When it comes up, it's going to look like this. D blank. It's going to be parentheses. And then it's going to say, I believe it says x equals and blank. All right. I think it says something like that. I'm going to show you what we're going to put in every place. Okay. We're taking the derivative with respect to x. We're going to put the function inside of there. You can also store it in y1 and put y1 there. Right. And then whatever x value we're plugging in goes right there. And that's how we do it. Okay. Okay. So Math 8 is called in deriv. All right, it's a numerical derivative. All right, so if you need the derivative of a function at 2.4, it'll tell you. If you need the derivative of negative 1.777777, it'll tell you. okay? So let's do this one together using the calculator. So we want to find x cubed at, the derivative of x cubed at x equals -2. In other words, we want f prime at -2. That's what I'm looking for, okay? So I'm pick my calculator up and find it. Okay, you're going to do it on the home screen. So math 8, which is in deriv. Yeah. Okay, mine doesn't have the bar. Does yours have the bar? Yeah. Okay, so my function was x cubed. So I'm just going to type that in there, x cubed at x equals, was it 2? -2. -2. And I hit enter. Okay, now mine says 12.00001. Guess what it is? It's 12, okay? What they're doing, the calculator, the program, is that symmetric difference quotient. That's how it calculates a numerical derivative. Remember when we did that? So it's calculated, or it's programmed to do those limits. So that's why you will get like that. Or you might get 11.999999999, okay? It's 12. All right, so we have to understand that part, that there is some error in terms of rounding, estimation, all that stuff, because it's a machine and not a human, okay? So it's 12. Isn't that lovely? I love that, okay? Especially when I have a gross function like x squared plus 27 over 4x to the 5th minus 5, okay? And nobody wants to do that. But notice how they extend the problem. It says to write the equation of the tangent and the normal line of f of x at x equals -2. So remember, this derivative is the slope of my tangent. Okay, it's the same thing. That's what we talked about yesterday. And to write the equation of a tangent line, I need a slope, and what else do I need? I need a point, okay? Well, they gave me the point -2 for x. How could I get the y value? Plug it into f. So -2 cubed would be -8. So there's my point. And so now I can write my tangent equation. Y equals my slope, x opposite x, same y. Right? How does it change for my normal? What did we say a normal was? It's perpendicular, so the slope is opposite reciprocal. So the only thing that changes is my slope, because it becomes -1/12, x plus 2 and -8. Okay. So what do you think about that? Not so bad? Okay. All right, I think you can do that next example, so we're going to skip it, all right? If it wants you to find the speed of the rock at t equals 1, that's an instantaneous rate of change. You're looking for a derivative, okay? So it's just a matter of interpreting what it's asking for, okay? Because they give you the equation, they give you the x or the t value you're going to plug in. You're just going to do a derivative, okay? So all you're looking for right here is s prime at 1. Speed would be an instantaneous rate of change. Okay, so that's what we're looking for. If we want to graph a derivative, good news, math 8 in y equals. All right, it works. Okay, so math 8 in y equals. Sometimes you're going to need to do multiple derivative graphs. Okay, that's possible. Or if, let's say, we're doing a multi-part question where I need the function and I need the derivative, you could also put your f of x in y1. And then in y2, you could do your math 8 and just put in the parentheses y1. Okay? Now, the only thing is we don't have a specific number that we're going to put in there. It's for all x. So for x equals x. That's the only difference. Okay? Because we're talking about every x value, not just one x value. Okay? So when we put it in y equals, we'll say it's for all x's. All right. So I want us to do example 14 together just to look at it. Okay. If we wanted to graph a derivative, it says let f of x equal ln of x. Use the numerical derivative to graph f prime. Could we guess what function f prime of x is by just looking at the graph? Okay. So jump over there. Let's go to y equals. Okay, and I'm going to clear that out, whatever's there. And I'm going to do math 8. Okay, so it pops that derivative in there, which is nice. We want to do ln, so ln of x, and then x for all x's. So I'm just going to put x again. Okay. I'm going to zoom 6 because I have no idea what shape my window's in, and it doesn't reset itself. So zoom 6. Oh, okay. So that is the derivative of ln. What does it look a lot like? What graph have we always done that looks like that diagonal? 1 over x. Okay, that actually is the derivative of ln. Okay, the derivative of ln is 1 over x. Okay, f prime of x is 1 over x. Do this one. Plug in f of x equals x cubed. This is one we did the other day. Okay. What do we think f prime is? Okay, so go back in. Okay, to your y equals, and let's just change that ln of x. Let me delete. To x cubed. Okay, and graph it. Oh, okay. What does that look like? Yeah, it's a quadratic. Okay, we got a quadratic. If we could zoom in, we would see that if we looked at the order of pairs, it was 3x squared, which is what we said it was. All right, on whatever day that was that we did that. Okay. All right, cool beans, that's it. Okay, so we're good with differentiability. Where are we not differentiable? What were those places where the derivative will not exist? Discontinuity, cusp, corner, vertical tangent. Okay, there's 4 of them. Cusp, corner, vertical tangent, discontinuity. So there's the places where it will fail to exist. What's the first thing you should check if you're trying to prove that something's differentiable at a point? Yep, does the function exist there? Okay, does the function exist there? Then we're going to look at the slope limits from both sides. Okay, math 8 is your friend. Okay, math 8 is your friend. All right, so for lesson practice this time. All right, on page 120 and 121, these are all about differentiability. 3, 5, 7, 9, 13, 27, 31, 35, 39. Okay, if you want to practice the math 8, on page 112, do number 20 with the calculator. Okay, so use an inderiv. You have a quiz Tuesday. It does not cover differentiability. Okay, so it's just over 2, 1 through 3. There's no differentiability on it. That's your limit definition. Okay, both of those, or maybe all 3. Okay, you do have a wrap up today, so let's get that done really quick. And if you didn't do yesterday's, be sure and get that done too. Okay, so get those done. All right, good job. Enjoy your long weekend. I'll be here hanging out with me, myself, and I. Unless your parents want to come visit, which I'm always up for.